Whatever it says on the folder, that's when it's due. And by the way, we finished section 5, so what should you do by Tuesday? Do the online quiz by Tuesday. And then just follow the folders. Whatever the folder says on the outside, that's when the homework's due. And now I've lost my... There we go. So now we're on number 6. Blood vessels. And then timing should work out perfectly so that I scare the hell out of you with one slide for the weekend, and then we can move on when we come back. Yeah, it's always nice to do that. You need to be scared at least more than once in one day. So vasculature and the blood pressure. You have to know these. Arteries, arterioles, capillaries, venules, and veins. In that order, actually. Why in that order? Because that's the proper flow of blood. It's a circulatory system and it always goes in a circle. What organ might you want to put here? Heart. What organ might you want to put here? Heart, right? So this is the pathway leaving the heart, going back to the heart. Where the capillaries are at, capillaries are in all the other ones. So if it's the lungs, there are capillary beds in there. If it's the kidney, there are capillary beds. If it's the liver, it doesn't matter. There are capillary beds. These are all the other organs. Doesn't matter if you're talking pulmonary or systemic circulation. Arteries, arterioles, capillaries of the organs, venules, veins, back to the heart. Heart leaves, pumping blood in arteries, back to the pathway. Always comes back with veins. Same path. You can see that. Doesn't matter if you take left or right side. Here you have the ventricle to the artery. Arterioles branch off. Arterioles always branch into an organ. When you see things at the surface of your skin, you only see arteries or veins. You never see arterioles, and you never see capillaries, you never see venules. They're called microcirculation. They're too small to see with the naked eye, and they're digging down into the tissue too. So you shouldn't even see them at the surface. So arterioles go into the organ. Those branch into capillaries, and the capillaries nurture the organ and clean up the waste, and they take that waste product and that deoxygenated blood over into... Well, I guess if we're collecting the lungs, it's not technically deoxygenated. It's oxygenated here. Into what V words? Venules. And then the venules flow back into veins, which always come back to the heart. And then you just follow the same pathway again. So at rest, you can see 100% of the right side of the heart goes to the lungs, but everything else has to be split through the systemic circulation. Look at some of these organs, like the kidneys. The kidneys are 1% of your body weight, but they demand about 20% of your blood flow. The brain's the same way. It usually demands about 16 to 20%. Your book is wrong. So 16 to 20% of the blood flow, but it's only 3% of your body weight. And then the muscles, they're requiring about 16 to 20% also, but they're the bulk of your body. It's not evenly distributed. It's distributed based on need. What's interesting is that each of these organs can demand their need. If the heart needs more blood, it'll pump that up. It'll crank it up to like 4 or 5%. Everything else has to take a hit because of it. If the brain needs more blood, it can turn it up, right? So what's the right order? You should know this. This is anatomy again. Correct organization of blood vessels is what? Okay, let's go to number 1. Arterioles to capillaries to venules to veins to the heart to arteries. Does that seem right? What's after arterioles? Always. Capillaries. What's after capillaries? Always. What's after venules? Always. What's after the veins? Always. Well, in the circulation. Heart. And then after the heart, always goes into the arteries. Does it seem right? It is right. Number 1's the right answer. What's wrong with number 2? Arteries to the heart. Arteries always leave the heart. You know number 2 is wrong. How about arteries to arterioles to the heart? No. How about arterioles to arteries to capillaries? What's wrong with that? It should be arterioles and arteries are backwards. So you know 2, 3, and 4 are wrong, and it had to be number 1. It's a circulatory system. It doesn't matter if I start with capillaries and work my way up. It's a circle. Write this down and put a star by it. You need to know this forever. If you ever take physics after this class, it'll give you an advantage too, because this is a physics term, or physics equation. When you see this in physics, it's always F equals P divided by R. F equals capital P divided by capital R, actually. Flow equals pressure divided by resistance. This keeps coming back. When we get to the lungs, we're going to use exactly the same equation. Why this is important, and I hate math, but I like to make equations like this simple. So what I do is I take and I plug in the ones, right? So if I take flow equals 1, pressure equals 1, resistance equals 1, does that math come out right? 1 divided by 1 equals 1? Works for me, right? It's exactly right. What if I double the pressure? So I go 2 divided by 1. Now what has to happen to flow? It turns to 2. If you double the pressure, what do you do to flow? You double it. If I turn pressure to 4, I take it 4 times as high. So now it's 4 divided by 1. What's my flow? It's 4. It's directly proportionate is the point. Anytime you do something to pressure, you have to do exactly the same thing to flow. If you double the pressure, you double the flow. If you quadruple the pressure, you quadruple the flow. If you quintuple the pressure, you quintuple the flow. They're directly proportional. But resistance opposes flow. So if you double the resistance, what do you think you do to flow? You turn it up or down? Resistance is the resistance on making it harder to push things through the blood system. It's hindrance is the technical word. It's a hindrance to flow. So if you increase the resistance, what do you do to your flow? You decrease it. If you double the resistance, so if I remember my equation, 1 equals 1 divided by 1. If I double this, what's 1 divided by 2? It's half. If I double resistance, I cut the flow in half. What if I take resistance times 4? What do I do to flow? I divide it by 4. If I take resistance and I make my resistance 16 times higher, what did I just do to my flow? I made it 16 times lower. Get the point? It's not the math that you have to worry about. It's the concept. I'm all about concepts. If you get this concept, it makes life so much easier. So as you thicken your arteries, you're increasing resistance. What are you doing to the flow through the arteries? You're decreasing the flow. If my heart beats harder, what did I do to the flow of the body? I increased it. You get it? It's the point. It's the big picture. It's not the math you have to worry about. All right, so a pressure gradient is the difference between 2 points. So if I take a blood vessel like, is this written in your notes, by the way? Perfect, I can go on. So if I take a blood vessel here, and it's 50 here and 10 down here, my pressure gradient is 40 millimeters of mercury. When we do in lab pulse pressure, that's a good example of it. You start with a 120 or an 80 pressure, and then you bump it up to 120. That difference is 40. That's the pressure you're feeling. What if I had a blood vessel and I doubled this? I don't necessarily have to double this end and this end, but I have to make sure the difference between these two ends is equal to that pressure. So 90 at one end, 10 at the other end, my pressure's 80. What did I do to my flow, by the way? If I doubled the pressure, what did I do to my flow? I doubled it. That's what this means down here. The flow is proportional to the change in pressure. Double the pressure, double the flow. You can see the flow over here is twice as big. If I do 90 to 10 or 180 to 100, is there a difference? It's exactly the same pressure, so what do you know about flow? Did the pressure change? Nope. Did flow change then? Nope. Flow stays exactly the same. So if the resistance increases, what happens to flow if the pressure remains the same? If the resistance increases, the flow has to decrease, right? If the pressure increases, what has to happen to flow? It increases. So to make flow, think about it this way. To make flow stay at 100%, if I want to keep flow at 100, and suddenly I'm adding a lot of plaque to my arteries, and I double the resistance, what do I have to do to pressure to keep flow at 100%? I have to double the pressure. So if my equation is 100 equals 100 divided by 100, but now my resistance is 200, what do I have to do to my pressure? I have to make it 200 also, right, to keep this at 100%. So 200%, or if my resistance goes up to 200% resistant, I have to go 200% pressure to keep my blood flow normal. Think of the blood flow to the brain. Does it want to go less than 100%? No way. So if the resistance is hard, if you block up the blood vessels going to the brain, what's the heart going to have to do to keep the brain happy? Double its pressure. It's the concept, not necessarily the numbers. So resistance is that word hindrance, so it's any hindrance to blood flow. It's friction, basically. If I'm red blood cells moving along this wall, the blood vessel wall, if I'm going nice and smooth flow, that's fine. But as soon as I grab a hold of the wall, what happens to friction? If I'm clinging on the wall, I create friction. What's going to happen to my ability to flow with this friction? It decreases. So if I have 10 millimeters of blood, and I have 10 millimeters in this little blood vessel, or this big one, which one's making more contact with the wall? The little blood vessel. So which one's going to be higher resistance? The little one. It's more friction in here. The smaller the blood vessel, the higher the friction. All right. This is where it gets nasty. Remember how I said if you double the pressure, you double the flow. If you double the radius, not resistance, if you double the radius or the size of the blood vessel, radius, remember, is from the center to the outside edge. If you double the radius, you have to take the resistance to the fourth power. Ugh. This is how this works. So if I take this one blood vessel here and I take it times 2, how do you take something to the fourth power? It's 2 times 2 times 2 times 2. So I've doubled it. So resistance was the R in our equation before. If my radius doubles, my resistance goes down by 2 times 2 times 2 times 2, by 16 times. So think of the big picture. If the common sense tells you if the blood vessel gets bigger, what happens to flow? It increases. But does it just double? If you double the blood vessel, does the blood flow double? No. It goes up by 2 times 2 times 2 times 2. The flow goes up 16 times. So does the size of a blood vessel make much of an effect on blood flow? Makes a huge effect. A little tiny change in blood vessel size makes a huge effect on pressure and flow. Why this is so important is that when your sympathetic nervous system squeezes your blood vessels, it only has to squeeze a little tiny bit to make a huge difference. So if I have this normal blood vessel here and I put a little epinephrine on it, and I give it a little squeeze, it makes a huge difference. I cut the flow down dramatically. Surface of the skin, a little adrenaline makes you go sheet white. So here's an example of the flow. And then last 2 slides and we're out of here because I have 1 minute left. The resistance is affected by 3 things, and I highlighted the most important of the 3. You have to know all 3, but there's one that we're going to keep talking about the rest of this class, or the rest of this lecture material. Viscosity is the thickness of the blood. The thicker the blood, what's it tell you about the resistance? There's more friction, so what's going to happen to resistance? It goes up. What flows easier, water or syrup? Water. Water's less viscous. Syrup is filled with proteins and sugars and particles. It's thick. Your blood is filled with proteins and red blood cells and white blood cells and platelets. It's thick. The thicker the blood is, the harder it's going to be to push it through, the more resistance. Next is the blood vessel length. The only times you really change the blood vessel length in your body is during puberty because you get taller, so you have to grow longer blood vessels, and then after puberty you don't get taller anymore, you get wider, right? So as you add fat, you have to add more blood vessels to reach out to the fat, which means you have to push further, which does what? Increases your resistance, which means your pressure is going to have to do what? Increase with it. That's why it's so bad on your heart to be overweight, because you have longer blood vessels, which means more resistance there. And then the last one, vessel radius, and I already talked about this. It's the major determinant of resistance. A little bit of radius change goes a long way. Viscosity takes days to change. You go to Colorado and it takes you a few days to make more red blood cells. Vessel length, that takes weeks. You eat a carton of ice cream today, tomorrow, the day after, and the day after that, and it takes you a few weeks to add those extra pounds, right? And then the blood vessels, though, I give you a little bit of adrenaline, I scare you a little bit, and suddenly, within milliseconds, it changes. So I guess I didn't get to leave you on that last scary slide, but there it is. Look at that math equation. And how about that one? Woo! We get to come back to that. Have a good weekend. Don't forget to online quiz number 5.